In Lesson 3, we're going to talk about the complex number system. Every number you're going to encounter in everyday life is a real number. That includes all of your fractions, all of your decimals, all of your irrational numbers, integers, everything you could possibly encounter in everyday life is a real number. Imaginary numbers involve square roots of negative numbers. Those are no longer real numbers because if you take a real number and square it, it will never be negative. However, imaginary numbers squared can be negative. The term imaginary was coined by René Descartes back in the 1600s because he didn't see any practical application of them. As it turns out, students going into engineering and aeronautics and stuff will find out that there are actual applications of it. Anybody studying differential equations will see that to get to the solution to certain differential equations, you will require the knowledge and understanding of complex numbers. So they do have their practical application as it turns out, but the term imaginary has kind of stuck. And Leonhard Euler is the one who first started using I to represent this imaginary unit, which is defined, as you see up here, as the square root of -1, also mentioned in the last lesson. So we're going to look at it in a little bit more detail here. First of all, let's look at powers of I, and just think logically. All of the same rules and regulations, if you will, of numbers and algebra should hold true. And these are just facts. It's the way it has to be based on the way things have been defined. For instance, I raised to the 0. Well, any non-zero number raised to the 0 is always going to be 1. Right? Just think about, I'm just going to write this off to the side here, like if I have 2 raised to the 0, that means 1. If I have 2 raised to the 1, that means 2. If I have 2 raised to the 2, that means 4, because in each case you're just multiplying by another power of 2. Or if you're working in the reverse direction, anytime you decrease the power of 2 by 1, so any kind of time you decrease the power by 1, you're really dividing by your base. So 2 raised to the 2, to move that down to 2 raised to the 1, I'm really dividing by 2. To move from 2 to the 1 down to 2 to the 0, I'm dividing by 2 again, which is also why with negative exponents, if I would have 2 to the -1, that's like taking this last number here and dividing it by 2, which is why 2 to the -1 ends up being 1 over 2, and so on. So let me erase all of this. And let's look at I. Well, I raised to the 0, just like all of those others, is going to be 1 then. Because any non-zero number raised to the 0 is 1. It satisfies the same property. What about I raised to the 1? Well, any value raised to the 1 is just that value. So I raised to the 1 is I. No different than x raised to the 1, or 3 raised to the 1, or pi raised to the 1. So I raised to the 2. Well, look back up here at the definition. I is the square root of -1. So if I square both sides here, this tells me that I squared has to be -1. And so for this second one here, this has to be -1. So we have 1, we have I, we have -1, and now I cubed. Well, I could think of that as I times I times I. I have 3 i's multiplied together. I could think of that as I squared multiplied by I. And you have 2 i's multiplied together. Take it times another I, and that gives you 3 i's multiplied together. But I squared is the same thing as -1. I see that from right before that. And so what I really have here is -1 times I. And so -1 times I is then -I. And so when you're all done here, I raised to the 3rd is the same thing as -I, and that's why. Get rid of this and clean it up a little bit. So I to the 0 is 1. I to the 1 is I. I squared is -1, and I cubed is back to I. So what would I to the 4th be? There's different ways you can think about it. I could think of it as I squared being multiplied by I squared, for instance, because I have 4 i's in a product. I squared is negative 1, and so what I have is negative 1 times negative 1 here. Negative 1 times negative 1 is positive 1. And so that is why I raised to the 4th is going to be equal to 1. So again, cleaning it up, I to the 4th is 1. I to the 5th would be the same thing as I to the 4th multiplied by I, because I really have 5 i's in the product, so I could split it up as I to the 4 times I to the 1. I to the 4 is 1, I to the 1 is I, and 1 times I is back to I. And really, to keep this process going, you could just think of this fact. Here's I to the 4th, here's 1. So if I take this side times I, that'll bring me to I to the 5th. If I take this side times I, that brings me to 1 times I, which is just I. Now look at I to the 6th. Well, if I take I to the 5th and I, both sides of this equation, times I, I'm going to get I to the 6th on the left, and it would be I squared on the right. Well, I already know what I squared is equal to. I just did that back here. And I squared is negative 1, and so I to the 6th will be negative 1. To get to the next level, I'm taking both the left-hand side and the right-hand side times I. That would give me I to the 6th times I is I to the 7. Negative 1 times I is negative I. The same thing as what I had back here, which is why I have them lined up this way. So you can kind of see how this pattern just keeps repeating. As you keep multiplying by I, you move from 1 to I, to negative 1, to negative I, back to 1, I, negative 1, negative I, and that just keeps repeating by the same logic. So I to the 8 is going to be 1, I to the 9 is going to be I to the 10 is going to be negative 1, and I to the 11 is going to be negative I. And repeat. Forever. It'll work that way. So now what would I to the 17 be? Well, using similar logic to what you just saw above, you could try to figure out, well, which category would it fit in? Would it be equivalent to I to the 0 and I to the 4 and I to the 8 and so on? Well, if you notice, I to the 0, I to the 4, I to the 8, the next one over would be I to the 12, then I to the 16, then I to the 20. Every 4, it's going to be up there. And each of these specific exponents is a multiple of 4. If I take I to any multiple of 4 for an exponent, it's going to simplify to 1. We're going to utilize that fact in simplifying problems like you see in example 1. I raised to any power of 4 is 1. And so when I look at I to the 17, I'm going to split that up. I'm going to think of that as I to the 16 multiplied by I, or I to the 1. Because I to the 17 means you have 17 i's in the product. So think of that as combining 16 of the i's together and then 1 I outside of there. The reason I combined the 16 i's together is because I raised to the 16 is just 1. 16 is a multiple of 4, so I raised to the 16 is 1. So in the end, this is just going to be 1 times I, which simplifies to I. If I look at part B the same way, I would say split this up as I raised to, well, the exponent 443, I know that 4 goes into 400 and 440, and so I'm going to use 440 here. 440 is the largest multiple of 4 that's still smaller than that exponent. And so I'm going to use I raised to the 440 times I raised to the 3rd, and so I know that this will simplify to 1 multiplied by I cubed is the same thing as negative I. And so 1 times negative I is just negative I. So I to the 443 is the same thing as negative I. So how do I deal with negative exponents? Again, I'm going to make use of the fact I raised to any multiple of 4 is always 1. So if I take I to the negative 23, I can multiply it by 1, and that doesn't change it. Well, 1 is I to the 0, or I to the 4, or I to the 8, or I to the 12, or anything like that. So in this case, I have I to the negative 23rd. So why not multiply it by I raised to the 24? I wouldn't want to multiply it by I to the 20 because that would still give me a negative exponent. But by taking it times I raised to the 24, that gives me I raised to a positive exponent of, in this case, 1. Again, since you take I to the negative 23rd times I to the 24, you would add the exponents there, just using your standard principles from algebra, and that gives you I to the 1. I to the 1 is just I. And so this simplifies to I. So with negative exponents, really what you're doing is multiplying by 1. You're not breaking it down into pieces. Instead, you're saying, what can I multiply it by to get me up to a positive exponent? And what you multiply by has to be 1 so that you don't change the value. And so in this case, you're always looking for the smallest multiple of 4 that is larger than the absolute value of this negative term. So since it's negative 23rd, you're looking for the largest multiple of 4, or the smallest multiple of 4, rather, that's larger than 23. In part D, that means that I'm going to be looking for the smallest multiple of 4 that's bigger than 45. That would be 48. So I'm going to take it times I to the 48. That gives me I raised to the third. I to the third, I know, reduces to negative I. In the end, every single imaginary number you deal with will have to involve just I. You should not have I raised to a power or square roots of I or anything like that. Every single imaginary number will involve an I, just a single I. So for instance, as it says up here, all complex numbers can be written in the form a plus bi. And the complex numbers really encompass everything. Every real number is also a complex number. Complex numbers is the set of all real and imaginary numbers combined. So if it's real, it's not imaginary. If it's an imaginary number, it's not real. Those are two disjoint sets that, when you combine them, make up the entire complex number system. So let's look at the next one. When we're combining complex numbers, again, every complex number can be written with a real component and an imaginary component, and you just combine like terms. When you're adding, subtracting, multiplying, dividing, but you're also making use of the fact that you know what I is equal to, so you don't ever leave anything in terms of an I squared or an I cubed or anything like that. Every single answer needs to be in the form of a real number plus an imaginary component, an a plus bi form. So for this first one, I've got real components of 5 and 7, imaginary components of minus 2i and plus 3i, and so combining the like terms, I can see that the answer is going to be 5 plus 7 for the real component, which is 12, and then minus 2i plus 3i, which is plus 1i, or just plus I, for the imaginary component. So the real component there is 12, the imaginary component is I. 12 plus I is what you get, just combining like terms. So it's really no different than if you'd have had 5 minus 2x plus 7 plus 3x. It's going to end up being 12 plus x in that case. So you're really handling it no differently than just adding two binomials. Same thing here, just combine like terms. So real components here are 5 and 7. Imaginary components are minus 2i and 3i. But in this case, it's a minus in between here. So I need to be sure to subtract the second numbers from the first. So for the imaginary component, or sorry, start with the real. For the real component, it's going to be 5 minus 7. 5 minus 7 is negative 2. For the imaginary component, it's going to be negative 2i minus 3i, which is minus 5i. And that would be your answer here. Negative 2 minus 5i. When you're multiplying them, you just distribute like you do if this were 5 minus 2x times 7 plus 3x. Just distribute. So 5 times 7, the first ones, 5 times 7 gives you 35. And then negative 2i times 7 would be negative 14i. And then 5 times 3i is going to be 15i. And then negative 2i times positive 3i is going to be negative 6i squared. Well, this is equivalent to 35 plus I, and then minus 6, and instead of I squared, I'm going to substitute what that's equal to, which is negative 1. Again, I want to simplify this completely, and if I would leave it with an I squared, it's not simplified. So negative 6 times negative 1 over here is positive 6. 6 plus 35, since those are both real numbers, I can combine them. 6 plus 35 is 41, so in the end, I have 41 plus I. And that's written in the proper form, your A plus BI form. Dividing complex numbers really boils down to simplifying a complex fraction, a true complex fraction, one that involves complex numbers. Not the compound fraction that is oftentimes called a complex fraction in many textbooks and in practice by many people. But now this is a true complex fraction, 5 minus 2i over 7 plus 3i. To simplify this and write it as something plus something times I, an A plus BI form, I'm going to need to multiply the numerator and denominator by the conjugate of the denominator, also known as the complex conjugate of the denominator. Since I have 7 plus 3i, I multiply top and bottom by 7 minus 3i. What this will do is produce a single real number on the bottom because it will eliminate the imaginary term. The middle term will drop out, and that will be the imaginary term, as we'll see here. So on top, multiplying that out, I'm going to have 5 times 7 is 35. Negative 2i times 7 is negative 14i. Negative 5 times negative 3i is negative 15i. And negative 2i times negative 3i is positive 6i squared. So there's my numerator. My denominator is 7 times 7 is 49. And then I have 3i times 7 is 21i. 7 times negative 3i is negative 21i. And 3i times negative 3i is negative 9i squared. So you can see these middle terms here are going to drop out. The plus 21i minus 21i. And so now what I have is on top 35 minus 29i, and then 6 times I squared is 6 times negative 1. That's negative 6. And on bottom I have 49 minus 9 times negative 1, which is positive 9. And so this is the same thing as, well, 35 minus 6 is 29, so on top I have 29 minus 29i. On bottom, 49 plus 9 is 58. This is not completely simplified yet because each of those terms can be divided by 29. So I could factor a 29 out of the top. Think of that as 29 times 1 minus I. I could factor a 29 out of the bottom, or the denominator. Think of that as 29 times 2. And then the 29 on top and bottom cancel each other. It's a common factor to the top and bottom, which leaves me with 1 minus I over 2. You could also think of that as 1 over 2 minus 1 over 2i to truly see the A plus BI form. So that's it for that page. With real numbers, you can display them all in a nice order on a line called the real number line. Well, you're still going to see the real number line here when we're talking about imaginary numbers, because they all have a real component and an imaginary component. All complex numbers have a real component and an imaginary. But to plot the entire complex number system, it requires plotting them in a plane in 2 dimensions now, since you do have 2 components to it. These 2 dimensions are forming up the plane here with a real number line and an imaginary number line, and this entire plane is known as a complex plane. So it's just like plotting coordinates, x and y coordinates, it's just now it's real and imaginary coordinates. So in example 3 it says plot the complex numbers that are inside the absolute value bars and evaluate the following absolute values. So I'll set up the complex plane here. Let me just do that in, say, purple. So here's my complex plane. I'm just showing that portion so I can really see the 3 plus 4i. So 3 is the real component, that's in the real direction. 4 is the imaginary component, that's in the imaginary direction. So 3 plus 4i is talking about this point right here. Straight up from the 3, straight over from the 4. And so this number right here is where you would actually plot 3 plus 4i. When we're talking about the absolute value of a complex number, also known as its modulus, we're talking about the distance to the origin. So we're talking about this length right here. And that's actually how distance is defined always. Even along the real number line, it's distance to the origin. So like when we say the absolute value of -5 is 5 units from the origin, and so its absolute value is 5. That's why absolute value is never a negative quantity. It's always 0 or positive. So in this case, I'm looking for the absolute value of 3 plus 4i. And that's going to be the length of this line segment here. I'll just call it A for absolute value. That's what I'm looking for. Well, here comes good old Pythagorean theorem. If I go straight over and straight down to have those points meet at perpendicular intersections here to form a right angle or a right triangle overall, I can see that this right triangle has a base of 3 and a height of 4. And so I know from the Pythagorean theorem that the hypotenuse, which is a squared, has to equal the base squared plus the height squared. So if I take 3 squared plus 4 squared, that has to be a squared by the Pythagorean theorem. The hypotenuse squared is the sum of the squares of the sides. And 3 squared plus 4 squared is 9 plus 16, which is 25. So now I've got a squared equals 25, which means a has to be 5 here. Algebraically, if all I saw was a squared equals 25, it could be plus or minus 5 then for a. But since I know a in this case is representing a length, I know it's going to be the positive 5. And so that tells me that the absolute value of 3 plus 4i is equal to 5. One thing to point out, whenever you take the absolute value of any number, it's always going to be a real number because it's measuring a distance. So the absolute value of a complex number such as 3 plus 4i will still turn out to be a real value in the end. So let's look at this one. We've got 1 minus 2i. So it's 1 in the real direction, negative 2 in the imaginary direction. So I'm talking about this point right here. And to find its absolute value is the same as finding the length of that line segment back to the origin. Once again, I'll just call this A, and then I'll set up a right triangle. Use Pythagorean theorem. This side has a length 1, this side 2. And so this tells me that A squared has to be 1 squared plus 2 squared, which is 5. So A in this case is going to be the square root of 5. And so that tells me that the absolute value of 1 minus 2i is the square root of 5. And that's all there is to that. And we can generalize to a formula that you'll find. A lot of times you'll find this formula for the absolute value of a plus bi or the modulus of a complex number, but all it is the Pythagorean theorem in a slightly different form. If I just generalize what I've just done, if it has a real component of A and an imaginary component of B, that would be A plus BI. The point would be right here. And so I would ultimately be finding the length of this line segment, the distance to the origin. And so set up your right triangle. The base has a length of A, the height is B, and I'm looking for this side, which I'll call a capital A. And the relationship here is that A squared has to be equal to A squared plus B squared. And that's a capital A squared equaling lowercase a squared plus lowercase b squared. And so A would be the square root of A squared plus B squared. And it's not plus or minus the square root again because it's measuring a distance, and distance is never negative. And so in the end, this formula is that the absolute value of A plus BI will always end up being A squared plus B squared square rooted. And that's just a direct result from the Pythagorean theorem. Pythagorean theorem is really arguably the most important theorem, important formula in all of Euclidean geometry. And so that's it for Lesson 3.